In section 16.8, we're going to extend our flux form of Green's theorem from two-dimensional space to three-dimensional space. So here in the top it says divergence theorem, flux form of Green's theorem in, and I don't know why, but three-dimensional real space was left off. So if you look at the diagram, we have our flux form that we had talked about in a previous section. So we could look at it in terms of a line integral. And then if we go into three-dimensional space, all we're doing is adding a dimension. So notice that that line integral is pretty much the same, but instead of over a curve, it's a double integral over a surface again, because we're adding a dimension. And then our Green's theorem double integral over the region, and it's a dA because it's an area of a region, adding a dimension becomes a triple integral over a volume. Okay? But it's the exact same integral. Again, we're just adding a dimension, which is what we see in the box below. Theorem 16.15 is our divergence theorem. If we have a vector field, and here our vector field, f, is simply a function of an FGH, right? So if we have a vector field F, then we can look at our divergence theorem, where the dot of the del operator with our vector field is simply the divergence of our vector field. When you compute the dot product, remember that's just the partial derivative of f with respect to x plus g with respect to y plus h with respect to z. So very short section, as was the previous section, because in these two sections, all we're doing is doing exactly what we've been talking about all along. We're just going from two-dimensional space to three-dimensional space. So we'll do a few examples. Example 1, we want to compute the net outward flux of this vector field, F, which is x, 2y, z. S is going to be the boundary of the tetrahedron in the first octant formed by the plane x plus y plus z equal to 1. Okay, so first of all, if I was going to use the del operator dotted with f, so that triple integral form, the first thing I'm going to need is I'm going to need to know what this divergence is. So first of all, it's simply the partial derivative of f, which is x, with respect to x, which would be 1, plus the partial derivative of g with respect to y, which would be 2, plus the partial derivative of h with respect to z is 1. And it's just 4. Looking at this triple integral over d, it's 4 dv. So going back to the very beginning, when we were looking at triple integrals and describing volumes, if you were to factor out this 4, the integrand is 1 dv, which is simply the volume of the tetrahedron. So if you don't know what the formula for the volume of a tetrahedron is, it's going to be 1/3 times the area of the base times the height. And if you don't know what a tetrahedron is, tetrahedron is a prism. It's all the sides are triangular. Let me go ahead and sketch this. So again, this is a XYZ. And this tetrahedron, if we were to find all the intercepts, it would be 1, 1, 1 for all of them. And this is in the first octant, so 1, 1, and 1. So that would be our tetrahedron. When we're talking about the base of the tetrahedron, it doesn't matter how you describe the base, so I'm going to let the XY plane be the base, but you don't have to. You could lay it on whichever side you wish. However, if this were the base, oops, I don't want that. If this were the base, then I would need the area of this base. So again, the volume of a tetrahedron is going to be 1/3 times the area of the base times the height. And the area of this base is going to be 1/2 because it's triangular, 1 times 1, which is simply 1/2. So it's just the area of that triangle, which means this tetrahedron is going to be, remember there's a 4 on the outside of this triple integral. So this is simply going to be equal to 4 times 1/3 times the area of the base, which is 1/2, times the height. So the height would be the maximum z value. In this case, it's 1. And I get 4/6, or 2/3. However, you didn't have to do it that way. If you want, you could have set up that triple integral. Just go back to the very beginning when we're looking at triple integrals and we're setting up the limits of integration. Remember, you're going to need to describe your x, your y, and your z. So in this case, if you did want to set up the triple integral, you could look at the z values going from first octant, so 0, and then take this equation of the plane and solve it for z, you get 1 minus x minus y. So 0 to 1 minus x minus y. Then if you're looking at the y value, set z equal to 0 in that equation and solve it for y, you get 1 minus x. And then the x values would go from 0 to 1. And I'm not going over how you come up with these limits of integration. That was in the very, very, very beginning when we were first doing our triple integrals. So you could do that. And you could set up that triple integral, which I'm not going to do. But you could do 4 times, I'll do x on the outside, 0 to 1, y, 0 to 1 minus x, and then 0, 1 minus x minus y, dz, dy, dx. If you did want to verify that these would actually be the same, you can go ahead and verify, but I'm not going to bother. Why don't we do another example? Example 2, it says verify the divergence theorem for the radial field F equal to xyz and the sphere S defined by x squared plus y squared plus z squared equal to 4. So that's just a sphere of radius 2 centered at the origin. So this sphere is going to enclose our region D. So D is boundary of the sphere and everything inside. We're going to assume our normal vector is an outward normal vector on the sphere. Because remember, we do need an orientation which determines your vector. Since it says verify the divergence theorem, what that means is that we have to use both forms, both the double integral on the left and the triple integral on the right. I'm going to start out with the triple integral over our region D enclosed by that sphere. And the reason why I'm starting with this is because I already know that I'm going to get a constant inside my integral, so it's just simply figuring out the volume, and it just becomes the volume of a sphere. So when we look at this dot, or the divergence of f, the partial derivative of f with respect to x is just 1, g with respect to y is 1, h with respect to z is 1. So this triple integral is simply 3 dv. Again, we have what we had in the previous example, where all we have to do is compute the volume and then times it by 3. So this is equal to 3 times the volume of the sphere. Or you could set up all those limits of integration. I tend to do things the easiest possible way. When we look at the volume of a sphere, it's 4/3 pi r squared. In our case, r is 2. This is going to be 3 times the volume of the sphere, which is 4/3 pi r is 2 squared. Okay, so that's going to be 4 times 8, 32 pi. Now remember, this divergence theorem, we're computing flux or flow. Although it wasn't asked for in these questions, this is a positive flux, so it would be a source, right? Now looking at the other form, which would be this double integral over S of f dotted with the normal vector, integrating over the surface, going back to previous sections, recall that on a surface integral, when we compute the normal vector here, when we're computing flux, we can just look at the cross of the tangent vectors with respect to a u and a v. But I have to be able to define a function r with respect to u and v. So I have my vector field, but I'm going to dot this with tangent vector with respect to u, cross tangent vector with respect to v, which is simply, right, the derivative with respect to u cross derivative with respect to v. Those would give me 2 vectors to cross, dA. So this is what I'm going to use. I need to describe this vector field in terms of r of uv so that I can actually find this normal vector. And since we're talking about x squared plus y squared plus z squared equal to 4, this is a sphere, we're going to go back to our spherical coordinates. And remember when we did transformations to uv, to write this as the vector. So just go back to that section. Our radius is 2, so it becomes 2 sine u cosine v. 2 sine u sine v. Again, we're just looking at the form that we had from a previous section. And then 2 cosine of u. So recall here that this is spherical, where we let u equal to phi and v equal to theta. So since u is equal to phi, in spherical, phi is going to go from 0 to pi, and v is equal to theta. Theta is going to go, for the whole sphere, it's going to go from 0 to 2 pi. So we'll do that later. Our normal vector, and again, we figured this out in a previous section. So instead of computing the derivative of r with respect to u, which would give me the tangent vector with respect to u, and then the derivative of r with respect to v, oops, sorry, I wrote u twice, which would give me the tangent vector with respect to v, and then crossing those, I'm just going to go to what this would be with radius 2, it's going to be 4 sine squared u cosine v. Again, we derived this before, so I'm just using what we had in previous sections. But you can go ahead and verify and compute this again. 4 sine squared u sine v, and then 4 sine u cosine u. Sine u cosine, well, I'll just write it in this way. Okay, again, this is from a previous section. I didn't want to compute it all again. So let's look at taking the dot of f with n. So remember the dot product, all we're doing is multiplying, adding, and I have these two vectors all nicely lined up. So when I multiply, I get 8 sine to the third of u cosine squared v, plus, multiply the next terms would be 8 sine cubed u sine squared v, plus, and then multiplying the last would be 8 sine u cosine squared u. All right, simplifying it. If you look at the first two terms and you factor out 8 sine cubed, what's left is a cosine squared v plus sine squared v, which is simply 1. So that would simplify to 8 sine cubed u plus 8 sine u cosine squared u. And now looking at factoring out 8 sine u, you'd have a sine squared u plus cosine squared u, which is just 1. So that's going to be the dot of fn, our normal vector n. Now recall that our u value, which was our phi, is going to go from 0 to pi. And our theta, which is our v value, goes from 0 to 2 pi. So I have all the information I need to set up my integral. It's going to be a double integral. I'm going to put theta on the outside from 0 to 2 pi, and then phi 0 to pi. This becomes 8 sine of u, and it's a du dv. Okay, so that was a lot of work. I like the first form much better. Integrand would be negative 8 cosine u, 0 to pi, and that's a dv. So that would be 8 minus negative 8, so positive 16. Which then becomes 16v from 0 to 2 pi, and I get 32 pi. So this verifies that it doesn't matter which side of the divergence theorem you use, you still get 32 pi. All right. In example 3, we have the question of computing the net outward flux. So if it says compute the net outward flux, and it's three-dimensional space, which I can see this x, y, z, then you're using the divergence theorem. So compute the net outward flux of the vector field F, which is xy, yz, 2z. S is going to be the surface of the cube that's given here for these x, y, and z values. All right, the first thing I'm going to do is I'm going to compute the divergence, which would be the partial derivative, and here we have our f, our g, and our h. Partial derivative of f with respect to x is y, g with respect to y is z plus h with respect to z is 2. And now my triple integral over d would be y plus z plus 2 dv. Oh, that's a 2. It looks like a z. What are my limits of integration? Simple. I'm looking at this cube, and my x, y, and z values are already given. Nicely constant limits of integration. So this triple integral is simply, and they all go from 0 to 2. It's a triple integral where x, y, and z go from 0 to 2. It doesn't really matter which one I integrate first, second, third, because they're all constant limits of integration. So I'm just going to do a dx, dy, dz. So this first inner integral is simply xy plus xz plus 2x evaluated from 0 to 2. 2y, 2z, and 4 should be my integrand. Plus, okay. So now integrating with respect to y, it looks like it's going to be y squared plus 2yz plus 4y. Again, 0 to 2. Let's see, that's 4 plus 4z plus 8. And I have the integral from 0 to 2 of 4z plus 12 dz. This is going to bug me because these are not equal. That's just scratch work. I should have done that somewhere else. Ew. Okay. I get 2z squared plus 12z evaluated from 0 to 2. Looks like it's going to be 8 plus 24 or 32. A lot of 32s. So I'm doing just a bunch of different examples so you could just see different regions and also the different ways that a problem could be worded. The next example, example 4, is actually going to be the last example we're going to do. We want to compute the net outward flux of the vector field given across the boundary of the region D, where D is a region between the spheres of radius 1 and 2 centered at 0, 0, 0, or centered at the origin. So I don't know if you recognize this. Remember, you can use everything from previous sections, but this looks to me like a radial vector field. So the first thing I'm going to do is I'm going to find my divergence. I need the partial derivative with respect to of f with respect to x, but we already did this in a previous section. Remember, this is just going to be equal to y squared plus z squared over the square root of x squared plus y squared plus z squared. And then g with respect to y is x squared plus z squared over the square root of, same thing, x squared plus y squared plus z squared. And then we have h with respect to z, which would be our x squared plus y squared over the same denominator. And And when you add all of these up, which again, we had done in a previous section, we get that our divergence is equal to 2 over the square root of x squared plus y squared plus z squared. So please, please use what we did in previous sections. Don't work any harder than you have to. Now I'm going to set up my triple integral over this region D. Now remember, it's just our divergence integrating with respect to volume. Now, when we look at our region, the region is the region between two spheres, one of radius 1 and one of radius 2. So since they're spheres, I'm thinking spherical coordinates. And so now this is simply a triple integral using spherical coordinates. So go way back again when we first started talking about cylindrical and spherical coordinates when we were doing our triple integrals. If I were to look at my theta values, it's a sphere, so it's going to go from 0 to 2 pi. If I was going to look at phi, 0 to pi, and then rho, which is like your radius. Since these spheres have radius of 1 and 2, my rho values are going to go from 1 to 2. And then now that I'm in spherical, think about this divergence. It's 2 over the square root of, remember, x squared plus y squared plus z squared is simply rho squared. And I'm in spherical, so it's going to be times rho squared sine phi. And I'm going to go d rho, d phi, d theta. And that's the power of this divergence theorem, is it allows us to go all the way back to the very beginning when we're looking at these triple integrals. Let's go ahead and compute this. Why don't I go ahead and simplify this to 2 over p, or rho, sorry, times rho squared. So that's just going to be 2 times rho sine phi d rho d phi d theta. So integrating with respect to rho first, this will become rho squared. And I'll leave out the sine phi since I'm treating it as if it were a constant from 1 to 2. Which would be 4 minus 1, so that becomes 3. So integral from 0 to 2 pi, integral from 0 to pi, 3 sine phi. Which then becomes negative 3 cosine phi. From 0 to pi, which would be 3 minus a negative 3, so 3 plus 3 is 6. D theta. Looks like it's going to be 12 pi. And that's all the examples we're going to do. Again, very short, similar to the last section, which was very short. And that's because all we're doing in these last two sections are going from two-dimensional space to three-dimensional space. We already talked about all the complicated stuff, did all that other stuff. Now we're just going up a dimension. The last thing I want to talk about is, again, we're not going to do any examples. This is just some topics that we should probably just touch upon. In theorem 16.6, it's the divergence theorem for hollow regions, and I could have used this theorem in example 4, because remember, example 4 was a sphere going from a radius of 1 to a radius of 2. So I could have used this theorem instead and just computed the outer. So here in this theorem, we're calling this our S sub 2. I could have just computed the integral for the outer, and in our case that was a sphere of radius 2, and I could have just subtracted the inner. Here in the diagram that would be the S sub 1, and broken it up into two double integrals. However, I felt it was easier just to do it the way I did it. So again, you're free to use this theorem if you wish. I also wanted to point out, since most of you are engineer majors, if there are some applications you may see in your physics or in your engineering courses, and we're not going to do any examples of this, but this is where you would see this flux or this idea of flow. Gauss's law should come up, especially if you're going into electrical engineering. So if you have a point charge, which would be this first diagram here, there's some charge, then it can be described by this equation where r is going to be x, y, z. And then this epsilon naught, E naught, this is just a constant that we call the permittivity of free space. So to compute this flow of electricity given this charge, you would use this Gauss's law formula, which is simply this double integral. And E is going to be considered your vector space here. Now, you may not just get a point charge, you also may get a distribution, Q. So you may have a density function. In that case, we still have Gauss's law, but it's a little bit more complicated. So that would be given by this integral here. Again, we're not going to be computing, but you might see it. Another common application would be in heat transfer. So if you have some temperature distribution over a solid body D, then the heat flow, again, flow is flux, can be seen with this vector field negative K. This is like the del operator of T, and Q just represents a source of heat. So it's similar to that other diagram where Q was a point charge. Well, this would be the same thing, but instead it's heat. Then you can use the following formula or integrals to compute the heat transfer or the flow of heat. So that would be it for our chapter 16. And then the last topics that we're going to discuss for this course would be differential equations.